Let's take a look at what happens when we put the object at the focus itself. Okay, so we're going to follow the same rules. So our first ray goes parallel to the midline. Parallel to the midline, hits the mirror, and bounces back through the focus. That's ray number 1. Ray number 2 goes through the focus and hits the mirror. So ray number 2 starts here, goes through the focus. And these two guys, they never cross. You get this weird place where there is no image. You can see this in a spoon. You can move your eyeball closer and closer and closer and closer. Your eyeball gets bigger and bigger and bigger until there's all of a sudden no image. And then everything goes really weird. So there is no image. And we can see that on this. So if we write this formula up, let's look at the math here. 1 over the focus is equal to 1 over the distance to the object plus 1 over the distance to the image. Now the object is at the focus, so 1 over the focus is equal to 1 over the focus, because they're the same thing, right? Plus 1 over the distance to the image. Subtract 1 over the focus minus 1 over the focus is equal to 1 over the distance to the image. 0 is equal to 1 over the distance to the image. This is impossible. There's no number we can put in here to make this math equation work. There's no number that can be put in here to make this math equation work. We can't put 0 in here to make it work. It doesn't work if it's 0. There's no equation. This does not work. There's no image. Image is impossible. Now the really oddball one. Inside the focus. Okay, so we started out the same way. Our first ray hits the mirror and reflects back. Okay. Our second one. Our second one, we actually kind of do it kind of backwards. We go from here. We start at the focus, so ray 2. We go up to here. And then we reflect it parallel back. I'm just going to draw it completely because we start back here. Look at these two rays. These two rays will never meet. They're divergent. They will keep spreading apart forever. So we have divergent rays. Divergent rays tell us we're going to get an imaginary image. But where does that image happen? Well, when we have divergent rays, what we do is we backtrace our reflected rays. So this ray here is reflected. So here's ray 2. It started here, went up, doop. So we backtrace the reflected ray with dashed lines behind the mirror. We backtrace the reflected ray. Now let's look at the blue one. This was our incident ray. This is our reflected ray. So do we backtrace this one? No. We backtrace our reflected ray. So we line up this guy here, And now we backtrace our reflected ray. And we get the image where they cross. So we're going to get the image right here. Not imaginary, they're called virtual images. Oh. So let's do our lost. What is the location of our image? In this time, the location is 1.8, negative 1.8 centimeters. The orientation is upright. The size, this one got bigger, right? It is now 3.3 centimeters. Plus 3.3 centimeters. So our magnification, well, let's figure out how tall this guy is. This guy's 2 centimeters. So our magnification is equal to plus 3.3 over 2. And I don't know what 3.3 over 2 is off by heart. I should. Really, it's 16.5. 1.65. So our magnification is equal to 165%. And our type is virtual. It's virtual because it had divergent rays. We had to do the back tracing thing. It's virtual because it's on the opposite side of the mirror. Okay, so now let's do our math thing with this and let's see if this works. See if our ray equation works, our mirror equation right here. So 1 over f is equal to 1 over distance to the object plus 1 over distance to the image. Our distance to the object is 1.9. 1.9 plus our distance to the image is 1 over negative 1.8. Okay. Oh boy, let's see what happens here. So 1 divided by 1.9 plus 1 divided by negative, oh no, divided by, where's my negative button? Negative this did not work out very well. Do 1 divided by my answer to get negative 34.2. Haha. This sure is all I get out didn't work. I got my focal length to be negative 34.2. That's a big mistake. Because it definitely isn't 34.2. Something's way off. I think it's because this is supposed to be positive still. Surprisingly. Let's change that to positive and see what happens. Nah, I still get a weird number. I know, I'm putting these videos up on YouTube, and here I am screwing it up. Oh, well. We'll put this as a question mark for later as to why this not work out so well. I've got a hint why it didn't work out. One of the reasons why it doesn't work out so well is because I use curved lines here, and these are way off compared to where the straight up and down line would be. And yeah, this should be way different. If this line was straight up and down, which you should do, you should just generally do a straight up and down line, this ray would go way up to here. So our guy would be like way over here actually. So that's why we're getting such weird answers, is because of this curvature here that I put in. It's a big no-no. I put it in just for clarity on the pictures, and it works out for the other ones because they're far away from because they're a little farther away from the curve. But once they get close to the curve, then it changes things dramatically. So this curvature affected this astoundingly, and I think this should be still a positive. That's going to get us the closest possible answer. Yeah. So if I change this to a positive instead of a negative, I get 0.9243 centimeters, which would put it like here. But if this was farther away, and I think this would be like somewhere back here, that would move that focus out to there. So I put this curvature in just to clearly indicate what type of mirror it is, and it does have some effect on our answer. We should just go to a dashed line. Let's not worry about it too much, though. Okay. So remember. So on a concave mirror, we're going to write a few things down here. It's a terrible concave mirror. If right here is our focus, and then right here is our about double center of curvature. The location of the object. If the object is in this area, outside the center, we're going to get a smaller inverted image. So, location of object. If it's in here, we're going to get smaller and inverted. And it's going to be real. In here, we're going to get larger. So if the object is between the center and the focus, we're going to get larger, inverted, and real. What if it's at the center itself? If it's at the center itself, we're going to get same size, inverted, real. If the object is right at the focus, no image. Then if the object is between the focus and the mirror, we're going to get larger, enlarged, upright, so same orientation, and virtual. And there you have it. You should be able to draw ray diagrams accurately, locate the location, the orientation, the size, the type, calculate the magnification, and use this formula here to indicate whether or not you did it accurately. And as you saw, don't have a curvature in your mirror like this. Don't have this curvature in your mirror. Go through the center line of the mirror. Straight up line. All right, so those were the concave ones. Next video, we'll take a look at the convex one. And remember these characteristics.